Disk and rod collision. A rod of length L and moment of inertia I rests on a frictionless surface. A disk of mass m slides towards the rod and will hit the rod at a point that is L/4 from one end. Before this happens, two students discuss what will happen after the disk hits the rod. Student 1 says, since the rod is not attached to the surface at any pivot point, it will not rotate but simply move because linear momentum is conserved. Student 2 says, since the disk is hitting the rod off-center, it will only rotate and not move because angular momentum is conserved. A. Indicate any aspects of Student 1's claim that are correct and explain your reasoning. B. Indicate any aspects of Student 1's claim that are incorrect and explain your reasoning. C. Indicate any aspects of Student 2's claim that are correct and explain your reasoning. And finally, indicate any aspects of Student 2's claim that are incorrect and explain your reasoning. E. For the next experiment, one of the students attaches a pin to the right end of the rod so that it can rotate but not move. Indicate which outcome will result in a greater angular velocity for the rod. So here's your pin right over here. The disk bounces back or the disk sticks to the rod. Briefly explain your reasoning without deriving an equation for the angular velocity of the rod. Student 1 is correct in saying that linear momentum is conserved as there is no external net force acting on the disk rod system. The only forces are the force that the disk exerts on the rod and the rod exerts on the disk according to Newton's third law, and those are internal to the system. Student 1 is incorrect in saying that the rod will not rotate because it is not attached to a pivot point. The rod will rotate due to the conservation of angular momentum. The disk has an angular momentum about the center of mass of the rod. Why? See the next slide. When it strikes the rod, some of the angular momentum is transferred to the rod and it will rotate. The amount depends on the type of collision. The angular momentum of the disk about the rod's center of mass is the product of the disk momentum, the distance from the disk to the rod's center of mass, and the angle between those two quantities. It remains constant until the collision, since as r gets smaller, as it gets closer and closer to the rod, theta and sine theta get greater, resulting in a constant angular momentum. Student 2 is correct in claiming that angular momentum is conserved. There are no external forces acting on the disk rod system to provide a torque. If there is no net external torque, then angular momentum is conserved. Student 2 is incorrect in saying that the rod will only rotate because angular momentum is conserved. The conservation of angular momentum does not imply a conservation of translational motion. Linear momentum is conserved as there are no external forces. The initial momentum of the disk will be shared with the final momentum of the disk rod system, so it cannot equal zero. The rod will translate. It will move in that direction. For the next experiment, one of the students attaches a pin to the right end of the rod so they can rotate but not move. Indicate which outcome will result in a greater angular velocity for the rod. The answer is the disk bounces back. Why is that? The angular momentum is conserved in both cases, as there is no net external torque for the disk rod system. For the case where the disk sticks on the rod, that's this case right here, the final angular velocity of the disk and the rod is the same because they're stuck to each other. The final total angular momentum is then I omega, that's for the rod, plus m, mass of the disk, L/4 quantity squared, that's the distance from where the disk hits the rod compared to its center of mass, and then omega. And omega is the same. This is also equal to the initial angular momentum of the system. When the disk bounces off the rod, the final angular momentum is I omega rod minus m L/4 squared omega of the disk. Why is that? It's because the disk moves in the opposite direction. It has a negative angular momentum. The final angular momentum of the rod needs to increase to make up for the loss in the disk's angular momentum, so it can still equal the initial angular momentum because it's conserved. Therefore, the angular velocity of the disk has to increase to make that happen. So this will give you your greatest angular velocity.